So let us continue our discussion of Planck's law. So previously we said that the monochromatic emissive power for a black body is given by this expression, right? Here C1 is a constant known as that is equal to 2 pi C naught square h. C2 is another constant that is equal to h C naught by k. Here h is Planck's constant. C naught is the speed of electromagnetic waves in vacuum, and k is the Boltzmann constant, right? Now this term has units watt per meter square per micrometer. Why? Because this is the amount of energy emitted by a black body per unit time, per unit area of its surface, and per unit wavelength range around wavelength lambda. Please note that in this unit, micrometer does not denote the value of particular wavelength, but it denotes a wavelength range. This is what we have to understand, right? So, and secondly, we said that based on this definition, we can simply write it as EB comma lambda is equal to dEB by d lambda. What is dEB? dEB is the amount of energy emitted in this wavelength range d lambda. And this wavelength range is a very small wavelength range taken around a particular wavelength lambda, right? So from this expression, we can also write it as dEB is equal to EB comma lambda d lambda. So amount of energy emitted for an infinitesimal range. So amount of energy emitted for a finite range. And this expression can be used for finding out the amount of energy corresponding to maybe a light wavelength band, that is 0.4 micrometer to 0.76 micrometer in case of electric bulb, right? So this is a very important law. It was given by Max Planck, a German physicist, who gave the Planck's quantum theory and later on won the Nobel Prize also for it. And this law has very important, that is useful characteristics, some very important useful characteristics. So let us discuss those characteristics one by one. The first feature of Planck's law is that if for a given temperature we find out the monochromatic emissive power for different wavelengths, okay, and plot them on a graph, that means we draw EB comma lambda versus lambda graph for a particular temperature T, we will find out that this function is a differentiable function, right? So this initially this value increases with increasing wavelength. It achieves a maximum, that is a peak, and then again it decreases. For example, if I talk of bodies at a room temperature, like the bodies which have temperature near about 273 Kelvin or 298 Kelvin, this maximum value is achieved for a wavelength lambda m equal to like 9 micrometer or 10 micrometers. Okay. Or if we talk of sun, the maximum value of monochromatic emissive power is achieved for lambda m equal to 5 micrometers, near about 0.5 micrometers, near about this. The first feature of Planck's law is that monochromatic emissive power is a continuous function of lambda. What I mean is that if we take Eb comma lambda for a particular temperature but at different values of lambda and then plot those values on graph, that is we draw a graph Eb comma lambda versus lambda for a given temperature T, we will find out that this graph is a continuous or differentiable curve. Okay. Now, as the value of lambda increases, initially Eb comma lambda also increases. It achieves a maximum corresponding to a particular wavelength. Let us call this wavelength as lambda m and corresponding power as Eb comma lambda max. And then as the lambda increases, it again decreases to a minimum. So, for example, if we talk of sun, so sun has a temperature of surface temperature of near about 5780 Kelvin. Okay, so for this particular temperature, the lambda m is near about 0.5 micrometer. So it is for this particular wavelength, which lies in maybe yellow color, that the sun is emitting the maximum amount of radiation. And for other wavelengths, like you can say ultraviolet radiation, the energy is little less, or infrared radiation, the energy is less. So maximum radiation is emitted in the light wavelength band. Similarly, if we talk of bodies which are at room temperature, for example, bodies having a temperature of 300 Kelvin, so this lambda m is like 9.72 micrometers, which lies in the infrared radiation band. So maximum energy is emitted in infrared radiation band, while in light, ultraviolet, or you can say radio waves, the energy emitted is comparatively less. Okay, let us see the second feature of Planck's law. The second feature of Planck's law is that area under the curve EB comma lambda versus lambda is equal to total emissive power of the body, of the black body. This means if this is the graph, this is the curve, then the area under this curve is equal to total emissive power of the black body. Let us see how. See, we know dEB is equal to EB comma lambda d lambda. Now what is this? Energy emitted in an infinitesimal wavelength range d lambda, right? So what I have done is that in the graph on the horizontal axis, that is the wavelength axis, I have divided this whole wavelength axis into very large number of small wavelength ranges. Okay. Now for a particular wavelength range d lambda around lambda, this is the monochromatic emissive power, right? So for d lambda, if we take the rectangular strip, that is the area under the curve, this area will be equal to EB comma lambda into d lambda, right? So this strip is also equal to DEB, right? So for d lambda, DEB is equal to the area of the strip. Similarly, for all the wavelength ranges, small wavelength ranges, the amount of energy emitted will be equal to the area of the rectangular strip, right? So if we will add all the rectangular strips, we will get the total area, and addition of rectangular strips means addition of DEB, right? So we will get the total energy emitted by the black body. But what is the total energy emitted by the black body? It is the total emissive power, which can also be written as EB comma lambda d lambda integral from the starting point of the wavelength range, that is 0, and the end point of the wavelength range, that is lambda 2, that is infinite. The third feature of this Planck's law is that as the temperature increases, the graph shifts upwards and towards left. Let us see what the meaning is. See, for a particular wavelength lambda, if the temperature is increased, the corresponding monochromatic emissive power will also increase. The third feature of Planck's law is that as the temperature increases, the curve shifts upwards and towards left. Let us see what this means. So here what I have done is I have plotted the Planck's law for two different values of temperature. So there is temperature T1 in blue and temperature T2 in red, where T2 is greater than T1. You can take this T2 as 5780 Kelvin, the temperature of the sun, and this as 300 Kelvin, the temperature of bodies inside a room. Okay. So obviously, first of all, as you can see, if we take the monochromatic emissive powers for a particular wavelength lambda for temperature T1 and T2, you will find out that E1 is less than E2. This is very correct. This is very correct. This is very obvious. How? The temperature is the strength of activities going on inside the atom. Which activities? The shifting of electrons from one orbital to the other. So if temperature is higher, frequency of this shift will be higher. And if the frequency of this shift is higher, the amount of energy produced will also be higher, right? So it is very obvious that with the increase in temperature, the monochromatic emissive power corresponding to a particular wavelength lambda will also increase. Now if monochromatic emissive power for each wavelength is increasing, the total emissive power will also increase. But what is total emissive power? Total emissive power is the area of the curve, area under the curve, right? So if initially temperature is T1, the area is this much, but when the temperature is T2, which is higher, the area is this. So area has increased, representing the increase in total emissive power. Secondly, if we talk of bodies at room temperature, so these bodies emit energy more in infrared radiation, right? 9.72 micrometer. But when we talk of sun emits more energy in form of light, 0.5 micrometer. So 0.5 micrometer is less than 9.72 micrometer. An observation, right? And the graph also represents this. When the temperature is T1, the lambda m is lambda m1. And when the temperature is T2, lambda m is lambda m2, which is less than lambda m1. So when the temperature increases, the curve shifts upwards and towards left. Shifting upwards represents increase in area, that is increase in total emissive power, and shifting backwards, shifting towards left represents decrease in lambda m, that is emitting more energy in form of lower wavelength radiations. The fourth, that is the last feature of this law, is Wien's displacement law. And what this law means is that the product of lambda m and t, what is lambda m? The wavelength corresponding to maximum monochromatic power. What is the T? T is the temperature of the surface in Kelvin. And what is this C? C is a constant and its value is equal to 2897.98 micrometer Kelvin. Let us see how this relationship is evolved. See, we know that EB comma lambda is a continuous function of lambda, right? So for a given temperature, if we want to find out monochromatic emissive power for any wavelength, we can do it by just substituting the value of lambda and T. So this gives that the curve is continuous and differentiable over the whole wavelength range. So if it is continuous and differentiable, then corresponding to lambda m, that is when the monochromatic power is maximum, the slope of the curve should be 0. So if the slope of curve is 0, we put dEv comma lambda by d lambda equal to 0. So when you will solve this parameter, when you will solve this equation, you will find out that lambda mt is equal to 2897.98 micrometer Kelvin. So this means that this relationship lambda m and t is a hyperbolic relationship. So obviously when temperature increases, lambda m decreases and vice versa. So just to summarize, there are four main features of Planck's law. First of all, Ev comma lambda is a continuous function of lambda. It initially increases, then it decreases. If the temperature is increased, the curve will shift upwards, representing an increase in total emissive power, and towards left, representing a decrease in lambda m. And this is very easily observed from physical situations. Thirdly, next, lambda m into t is equal to constant, that is, it is a hyperbolic relationship, and this feature is known as Wien's displacement law.